It's safe to say multiplayer games have grown quite popular in recent years, although developing games with a multiplayer aspect can usually be the most challenging. Thankfully, these tend to be the most rewarding too, as adding a multiplayer mode to your game can encourage social interaction, bringing people together either collaboratively or promoting healthy competition, or at least you'd hope for it to be healthy. When implementing an online or networking element into your application, it generally means ensuring all clients in the session are in sync with each other. In a game, this could involve solving how a player's death affects all other players across the same session. In a collaborative application, such as a design board tool, this could mean ensuring that each user's cursor is correctly updated on everyone's screen as they perform actions on their local instance. In both cases, enabling such rich experiences requires constant real-time communication between all connected clients, while ideally ensuring there's only one source of truth between them, something not normally available applying the usual web practices. So developing an application or game like this for the web tends to bring its own set of challenges. Today we'll discuss a couple of these challenges and explore some of the patterns and architectural choices that might address these problems. So why not join me in an attempt to tackle some of these and develop an application that uses web technologies to allow for online communication between multiple clients. My name is Anthony and I like to build software in the browser using the latest technologies. As mentioned, developing online applications is not a simple task and comes with many problems that require solving, especially if not approached correctly. Before jumping into solving some of the specific gaming challenges, it's always best to familiarise yourself with the technologies you'll be using. Let's start with the basic web communication practices to ensure we're all on the same page. At a high level, standard web communication works over HTTP and is a wrapper for the actual network protocols, namely TCP, IP. When a browser sends a request to the server, which could be driven by a user navigation event or from a URL embedded within the HTML for example, you will attempt to handshake with the server. Successful or not, you will get the necessary response and include the corresponding HTTP status code and data. Once the response is sent however, the connection with the server will be dropped, meaning the browser will have to reconnect again if a further request is required. The advantage here, due to the underlying TCP protocol, is that we'll have the confidence that this response is guaranteed and any data will be in the correct order once returned. This benefits the web considerably. For example, you probably want to see a website showing all of its returned elements in the correct sections of the page layout. However, the downside to this guaranteed method is the overhead that this brings with it, and therefore can be considered slow, especially if the browser has to keep reconnecting to the server to retrieve new data. As you can imagine, this doesn't sit too well with our goal of developing an online game, as this requires a constant near-instant real-time communication to keep the game running smoothly. Due to our game requiring live updates, this method would almost certainly result in latency issues, even on the fastest of servers due to the high level of requests. Thankfully, things have evolved, and we now have alternative solutions. One such solution is long polling. The idea here is to keep the TCP connection open between the client and server for as long as required. This allows the server to delay its response to the request from the client and collect the necessary data so it can return it in one hit, removing the need for individual responses and reconnects. Another advantage is that it also eliminates the need to send empty responses due to the lack of changes, something that would normally happen with instant replies in standard traffic. However, even with this extra control, the high latency issue will more than likely remain. For online gaming where real-time information is required, speedy responses are the utmost importance. Unfortunately, neither of these solutions provide exactly what we need. This is where WebSockets come into play. WebSockets have been designed to be used for applications that require real-time communication, and therefore provide several advantages over conventional communication methods on the web. Once a WebSocket connection has been made, this will be persistent and allows for a reliable way for bidirectional and asynchronous communication to be made between the server and its connected client. This means the connection will stay open for traffic until either end terminates it, for example when there's been a disconnection or a timeout. This type of connection is often referred to as a full duplex data transmission, in that both sides can simultaneously send messages without collision or blocking issues. When initiating a WebSocket connection, the client will send a specific request asking for the browser to switch to this protocol. If it recognizes this request, it will accept it and perform the handshake with the client, opening the WebSocket connection. Once this is complete, the client and server can now communicate on this channel separately from other browser requests. As mentioned, this allows for a constant stream of independent messaging in real time. Using a server in these type of connections also means that it doesn't necessarily have to be a one-to-one communication either. The server can be used as a source of truth, broadcasting the required data across multiple connections and clients. This is perfect if you wish to keep all the clients in sync with each other, for example in a chat application, or more important for my channel, online gaming. There's a lot to be considered when implementing the WebSocket protocol, especially in large applications where maintaining thousands of concurrent connections can be possible. So understanding how best to apply it, primarily on the backend where other resourcing factors can come into play, such as performance, logging, retention, or even specific use cases, can take a great amount of effort. So as per usual, it's usually far easier to build something simple to get your feet wet before diving into the deep end. For this reason, in today's video, we'll be developing a basic chat application to familiarize ourselves with the WebSockets protocol and put its underlying technology into practice. The idea is that this application provides all the fundamentals for writing real-time online communication between the client and server. Speaking of which, we'll also build a server to keep the source of truth we've been looking for. Ultimately, the foundations of this project can be used as a base for other projects, such as online games, something we'll be covering in a future video. Do note, however, that I don't want to be bogged down with security or user authentication context in today's video, so we'll be leaving them out for speed. However, if you ever plan to publish what we built today, this is something you should seriously think about implementing before doing so, but more on those specific topics in a different video, I guess. Okay, enough talk. Let's get our hands dirty with some code and start by opening up our code editor of choice and setting up the project folder. Note that I've just created an empty folder on my machine called Chat Server and opened it up here in VS Code, which is what I'll be using for this video. As we'll be creating both the backend server and the front-end web application in this tutorial, let's first create two new folders so we can house the associated code for each of these projects separately. I'll keep it simple and call them client and server. Normally we jump into developing the application first, but instead we'll focus on setting up and configuring the server project. The main reason for this is that I prefer to ensure we have something to communicate with, and to be fair, we don't necessarily need a full front-end client to prove that. As the server will obviously be running on the back end, we could actually use any language that allows us to host a HTTP server. However, for this project, we'll continue to use JavaScript as this is what the channel is most known for. This might be controversial to some, so by all means, if you prefer to use something else, such as Go, Python or Rust, etc., then by all means please do. For this video though, we'll be using NodeJS as the server runtime, and its module manager, npm, to manage this. I won't be going into either of these tools in great detail here, but if you're coming from a front-end or JavaScript full-stack background, you're probably already familiar with both of them. If you don't currently have these installed on your machine, please first visit their site at nodejs.org and download and install the recommended LTS version. Don't worry, we won't need any specific version for this tutorial, so the latest version should just work fine. Once installed, you should be able to run the following commands from the terminal to get their versions. This just ensures that they are working as expected. For reference, here are the versions I'm currently running at the time of this recording. Okay, we should be good to continue. Open up a terminal and change folders to the server folder. From here, we'll first initialize an npm package dependency file. You can do this by using npm's init command. npm will then ask you a series of questions so that it can automatically configure this file for you. I specifically set the name and its description. For the rest, however, you can simply press enter to keep the default value, which is shown in brackets. Alternatively, you can just use the -y parameter, which will automatically create the file with all the default values. Either way, this should create a package.json file in the root of our server folder. If we were to view this file, you should be able to see the properties and values npm has set for us. Take note of the main and script properties here. The main property tells npm which file to be used as the entry point for our server code. This points to an index.js file that we don't currently have. Within the script object, npm has created a test definition by default, but honestly, we won't be using that today. Okay, let's look to fix these before moving on. First, we'll create the index.js file the package is expecting, and then replace the test property with our script that we'll use to start the server. For obvious reasons, let's call the script start, which we'll use to run the node runtime with the index file. We can now use this from the command line to start the server. Even though Node.js does support HTTP out of the box, it unfortunately does not have native WebSocket support built in, which to be fair makes sense as WebSockets are primarily a browser technology standard. We could just go ahead and implement our own WebSocket protocol, but then we would have to spend the next unknown amount of days trying to understand this thing. Jeez. Thankfully, there are many npm packages available that have done this work already and provide us exactly what we need. For the tutorial, we'll use a package called WS, which is lightweight and has good support and backing from the community. So let's go ahead and install that. While we have the package file open, we can manually add this to the dependencies object property like so. At the time of recording, the latest version is 8.18.0. Once added, we can tell npm to add it to our project using the install command from the terminal. This will download the package and store it in a Nodes module folder automatically for us. As we'll be using the ES module syntax in this project, the last thing we'll need to do is let Node.js know that we'll be doing this, as it does not expect this by default. simply add the type property and give it a value of module. Okay, with the project set up and the WS dependency now available, let's use it to create and host a WebSocket server locally on our machine. In the index file we've created, let's import the WebSocket server function from the WS package and simply assign a new instance of it to a variable. In this function, we'll also need to tell it which port we wish to host the server on. We'll pass in an object and use port 8080, although you can choose your own port number if this collides with something else on your machine. We'll next log a message out to the console, detailing that the server is now running. You don't necessarily need to do this, but I do feel it's good practice so that we have feedback from the server that we can analyze. For this reason, you'll see me do this throughout the tutorial. I'm also using the address function to return the actual port the server is using, just to confirm it is what we expect. To test that everything is working as expected so far, let's tell npm to run the start script we just set up. We can do this by simply entering npm followed by start in the terminal, like so. If all is well, it'll log out the message we entered, along with the expected port number we configured, and in this case, it seems so. However, the server is not doing much else at the moment, so let's extend this to listen for incoming connections. The WebSocket server has several events available that we can hook into, enabling us to add callbacks to them. For incoming connections, we'll be using the connection event full enough. This event will trigger each time a client has established a connection to the server. Again, just to prove this callback function triggers, we'll log out a simple message to the console. Let's quickly test this by restarting the server with npm start in the terminal. The usual starting message will be logged to the console and do nothing more, just like the previous test. However, it is now listening for incoming connections, so let's open a browser window and attempt to connect to it. In the browser console, let's create a new instance of the WebSocket object and pass on the URL of our WebSocket server. As we're running the server in the background locally, we're able to use localhost here. The browser should now successfully connect to the server and provide us with a socket connection to send messages with. You can confirm this by logging out the instance we created to the console. From the properties, the first thing we can see are the events available that allow us to respond based on messages received from the server. More on these later though. The ready state, which has a value of 1, this can be interpreted as successfully connected at the moment. And then finally the URL, which is now currently using the WebSocket protocol prefix. Just to prove the server has accepted this connection too, you'll notice the console has logged out the message we expected. Nice! We have successfully initialized the server and connected to it from the browser. In fact, we can do this multiple times, either from another tab or a new browser window, and we should again get another connection to the server, as you can see here. This proves we can have multiple browser or client instances communicating with the server at the same time, without any issues. Good stuff. Let's take what we've learned and move it to our project code, so we can make this a little more automated. Until now, we've just been working with the server and its respective folder. However, let's now move our focus to the client folder and start to flesh out the code that will run in the browser. Just for transparency, we're using a mono-style repo today, where we're holding both the client side and the server side code in the same project. You don't necessarily need to do this, but for the sake of today's video, it does make my life a little easier, so if you wish to split them out, please go ahead. Moving on, let's give the client its own index.js file, and inside this, like we did in the browser console, we'll create a WebSocket instance. However, this time we'll properly define the server URL, using a URL object with the correct WebSocket protocol. For the code to work in the browser, we'll also need to add an HTML file, and reference the index.js file as the entry point, so let's do that too. Here we'll define a basic HTML structure, and add a script element pointing to the index.js file we just created. Note again that I'm using the type of module to allow us to use the ES module syntax. As per usual in my tutorials, I'm using a live server extension within VS Code to host the client-side code on port 5500. I'm assuming you're aware of what these are, but if not, please see the video link I've included above, where I go into more details. Either way, I generally have this running all the time, and have it visible in the status bar at the bottom of the window. Before moving on, let's quickly ensure we're in a good place. Open up a browser and navigate to the index file hosted on the client URL. We're not doing anything with the HTML yet, so the page will be blank. However, if we open up the DevTools and inspect the Network tab, when refreshing the page, you will get the details that the WebSocket connection has been made. In simple terms, the local host entry shown here is the web page performing the WebSocket handshake with the server, while the WS entry is the actual WebSocket connection that has been created by the browser itself. If you prefer, we can single out the WebSocket traffic using the WS button along the top of the network timeline. Again, we can confirm the server has accepted this connection, as it has logged out the usual message to the console. Also, if we open up multiple tabs, each will still open their own connection just like before. Good stuff. We now have a client that is communicating with our server. But what happens when the browser or client is closed, or somehow becomes disconnected? Let's investigate how we can handle those type of scenarios next. Jumping back to the server code, as we're now looking to handle more than just the server connection event, we'll start by moving our current code over to a new function for readability purposes. I've named this connect client. We can then simply call this function within the connection callback function. Okay, so moving forward, we'll now need to reference the incoming client WebSocket, which the server provides through its connection parameters. So let's add this to the callback. With this, we can add event callbacks to the WebSocket, so that they can be called when those event messages are received. To add these callbacks, we can use the on function supplied on the socket itself. When the client does disconnect from the server for whatever reason, a close event is triggered. So let's subscribe to this using the socket's on function and add a new callback function, disconnect client. Again, we'll simply log out a message to the console to ensure this event has been triggered. And that's how simple it is, honestly. Note that I've simplified the messaging here in both events for a little more clarity. Just to prove this, we'll quickly test it. We start the server from the console using npm start again to ensure we're running the latest code. Then in the browser, open up a new window or tab to the hosted client URL and simply refresh the page or close it. If all is well, you should see both the connected and disconnected messages in the console. As you'd expect, the browser is cleaning up after itself once the tab is closed. This means it's also closing the WebSocket connection and sending a closed message back to the server. As per usual, we're able to do this with multiple clients, so you will again see the corresponding event messages appearing in the console. However, as you may have noticed, messages from clients can come in any order depending on the sequence of events. So right now we have no way of identifying which connection or messages relate to which client. Let's look to make more sense of this moving forward. Generally, when using a server-client relationship, you'd have some sense of server state. This is usually used as a source of truth to ensure any connected clients are kept in sync, both with the server and between all the clients themselves. We'll go into this more later, but for now, we'll simply create a state object with a client's property. This will be an array and hold a reference to all the instances of the WebSockets connected to the server. To keep tabs on each of these, we'll assign each WebSocket a universal unique identifier as they connect. The easiest way to do this is use the random UUID function provided by NodeJS's crypto library, which will give us a random but secure identifier string. So let's first pass on the socket parameter to the connect callback function and update it with an ID property within that function. We'll import the random UUID function and use it to assign the ID value. We'll also amend the console message to log out the value that was used for reference. We'll also push the socket to the state's client array, so we have a reference to it. Let's also mirror these changes to the disconnect callback function and console message too, for consistency. Although this time, rather than pushing to the client array, we'll remove the socket reference by filtering it out based on the socket ID. Again, let's quickly test these changes using the browser. Navigating to the same URL and refreshing the page, you should now notice the console has logged out the same connection messages, but this time it includes the assigned ID for the WebSocket. Nice! We can now use these to easily identify which client is connected and disconnected. Okay, let's make this a little more interesting by actually sending our own defined messages back and forth between the client and server. We'll start with the client by sending a message to the server. This can easily be done with the WebSocket send function, so let's quickly test this out by doing so as soon as we've successfully connected. This function takes one parameter, which is the actual data we wish to send. As you can see here, this could be several things, but we'll stick with strings for today's tutorial to keep it simple. In our test, let's be polite and simply say hello to the server. However, as the connection to the web server is asynchronous, the socket probably won't be available right away. So let's be a little hacky for now, just so we can prove the test works, by wrapping it within a timeout. We'll give it 5 seconds, which should be plenty of time for the WebSocket connection to be created. And to be fair, that's all we have to do. Although for the server to acknowledge this message, we'll also need to set up another event callback, so that it too can acknowledge it. So moving back to the server index file, we'll follow the same process as before, and add a further call to the WebSocket on function. This time however, we'll be using the message event. This event, as you can expect, is triggered when a message is received from the socket. Its callback will pass the data received from the message through its parameters, which as mentioned, can be multiple things, so this is the actual raw data sent by the client. So let's forward this on to our handler function, along with the socket itself. I've called this handle client message. Inside this function, we'll follow the usual practice and simply log the data out to the console using the socket ID, again to understand which client sent the message. Note that we're using a template literal for the console log, so the raw data will automatically be converted to a string. Okay, let's test these changes. We'll quickly restart the server again, using npm start in the console. and then refresh the client page in the browser. Within 5 seconds of the connection being made, you'll notice the server has logged out a message received from the client. Great stuff. However, at the moment, the server has been a little arrogant and not responding. Let's do the gentlemanly thing and get the server to say hello back. In the server code, in the sockets message handler callback, we'll simply use the same send function, but on the server side, to send a reply back to the client. For the browser to acknowledge this message, we'll also need to apply the same process as we've done on the server and set up an event callback. So on the client side, we'll add an event listener to the socket, again using the message event. We'll also again log out the result received to the console. The difference with the message received by the browser, however, is that the data is wrapped within a message event object. So let's perform another quick test and understand what's included within this object. We'll again restart the server, and after 5 seconds, the browser sends a hello message to the server, and instantly, the server acknowledges this and replies with its own hello message. If we open up the browser's DevTools, you'll find the message event object is logged to the console as expected. If we were to open this up, you'll notice quite a plethora of data is inside. Most of these are standard event properties, but what we want to focus on is the data property, which is the actual message sent by the server. One thing to notice is the timestamp property. This is the timer that constantly increases once the connection has been made. This can be useful for sequence purposes. There are other properties here that might be of interest, but for now we'll move on and update the console log to use the data property. Now when we refresh the browser, it simply displays the message text received from the server instead. Just as a side note, one thing you may have noticed is that we're using the same subscribe model to trigger the event callbacks both on the front end and the back end. And while on the subject of subscribing, if you're enjoying this video, why not subscribe to my channel too? It really would help me out, thanks. Anyways, as a final test, let's get the client and server to keep the conversation going indefinitely and try to replicate a real-time communication that WebSockets are best known for. On the client, we'll copy the timeout code and paste it into the message handler function. This will send another hello message to the server, which in turn will respond, causing a chain reaction. Let's also change the timeout to 2 seconds to speed up the responses. We could actually remove the timeout completely here to have instant replies, but in terms of this test, it would be difficult to see the responses, as it would just result in a flood of messages to the console on both sides. Okay, refreshing the browser now, as you can see, both the server and client are constantly sending and responding to the messages being received. We can also untick the grouping option here to improve the visibility of the messages in the browser console. Nice. So there you have it. We now have a basic structure and the event set up to handle bidirectional messaging between the client and server. Okay, let's take this one step further and use what we've learned to put this into something a little more useful, like a basic chat application. Most, if not all of us, use a chat application at least some point every day, be it through Facebook, Instagram, WhatsApp, Slack, Discord or even Steam. So I assume everyone knows how they work and that their UIs generally follow the same stacked message list approach. This will be something we'll look to simulate in our small project too. With that in mind, I'm going to copy over some initial structured code into the client's HTML index file. The top half of this is an unordered list element that will hold all of the messages. You'll notice I've added 2 test items or messages already, one for the inbound and another one for the outbound message. I've done this to ensure our styling classes are correct before moving on. The bottom half is a simple form element that allows users to enter their chat message. This includes a text input box and a submit button, both of which follow the standard HTML form practices. Lastly, take note that I've given both of these DOM elements an ID value to allow us to easily reference those and their child elements within our JavaScript and CSS code. Speaking of which, let's now add a new file to hold those CSS styles. I've called my file styles.css. Yep, nothing like plain naming your files. Again, I've already prepared some initial styles, so I'll copy them over here to speed things up a little. Please freeze the video if you wish to use these also. Note that I'm using standard CSS nesting and layering practices here to keep the styles somewhat readable. Once done, we'll add a reference to this new file in the head of our HTML file so that it loads the styles at runtime. Let's save all the changes and head back to the browser to see what we have so far. Refreshing the hosted page should show something similar to what we have here. I've not gone overly fancy with either the HTML or CSS styles, but what we do have should be enough to give us the basic tone of a chat application. As described, we have a chat message list covering most of the browser's window at the top, with a simple text box and send button at the bottom to allow users to enter and send a message. Notice that we also have 2 test messages as mentioned that use the styling for both the inbound message in grey and the outbound message in blue. All messages will stack from the bottom to replicate how most chat applications work. So far so good. The general idea is that we want to allow users to enter messages into the provided text box and submit them to the server, similar to what we've been doing automatically until now. The server in turn will receive those messages and then broadcast them to all users connected to the chat instance. This includes the original sender. Once the messages have been received by the clients, they will be added to the message list at the top of the window. You might think this is a little weird at first, but this keeps the server as a source of truth and all the connected clients in sync. More on this later, but let's jump back to the code and amend what we've done to get this working in practice. We'll start with the client code first and collect the message the user has entered into the text box once they submit it via the form. Let's remove both the timeouts as they've served their purpose and are no longer required. Although before we continue, let's bring up the HTML file so we can use it as a reference for the elements we need to access. We'll get an instance of the text box, which we can do by using the form's elements property. We're using the form's chat ID and the input's message name attributes here. Then we'll add an event listener and callback to the submit event on that form too. This means whenever the user clicks either the send button or presses enter on the text box, this callback will be triggered. Inside the callback, we'll first call the prevent default function on the event, which will stop the default submit behavior from happening, allowing us to override it with our own code. Next, we'll ensure the WebSocket connection is actually open by using its ready state property and the WebSocket's enum open value. So if we don't have an open connection, then there's no point in continuing, so we'll just exit early. However, if we do, we'll take that value entered into the text box and send that to the server. Then finally, if all is well, we'll clear out the text box by setting its value to an empty string. In fact, we'll also ensure the value contains at least one character before continuing, as sending blank messages is probably a bad idea too, honestly. One important thing to notice is that we've not updated the UI yet. This is because we want the server to be the source of truth. So moving back over to the server code, let's now update the handle client message function to handle a message sent by the client. As previously mentioned, as the server doesn't actually know the type of data the message contains at this point, we'll call this raw data instead. We'll update all instances to use this value, and then wrap it in a string constructor within the send function. This is to ensure we convert the data to a string data type before continuing. This will send the message back to the client, so let's now update the UI once this message has been received. In the client's handle server message function, we're going to add a new message item to our chat window's list element, simulating what we have already. Let's create a new instance of a list item element using the document's create element function. Then, as we know this is an outgoing message, we'll add the corresponding CS classes to it using the class list. Next, we'll then set the inner text to be the data received from the event, which we know is the original message text sent to the server. Lastly, we'll need to add this new element into the DOM within the chat window. To do this, we'll first add a new reference to the UI element using a query selector, as we know that is the parent. Once we have this, we can simply append our new message item as a child to that element. Okay, with that, let's check the result in the browser while ensuring the server is still running. In the text box, let's write a simple hello message and press enter, which will send the message onto the WebSocket server. Notice the server has received the message and in turn sent a response back to the client, which it has received, and added a new message element to our chat window with the outbound styling. This should work for every message we enter and send. Nice. Okay, let's try opening another browser window and connecting it to the WebSocket server URL. Notice when we send a message from either chat window, the other window does not receive the message. This is because we're using the sender's WebSocket connection to send the message back, meaning it's a one-to-one communication, which is obviously not what we want. Let's look to quickly fix this issue. Back in the server code, we'll replace the send call with a new broadcast message function. This function will be used to iterate over the connected clients and simply send, or rather, broadcast the message to each one of them. We'll do this with a for loop using our state object, which we know contains a client array holding all of our connected WebSocket instances. Now if we check the browser for both of our clients, if we send a message from one, both should receive the message as you'd expect. Although we now have a new problem to solve. Regardless of which client we send the message from, we're assuming they are always outbound messages. Normally, only the sender's message would have this styling, whereas other connected clients would usually have the inbound styling. However, the issue at the moment is that we really don't know which client initiated the original message. So let's look to change that by tackling how we send our messages a little differently. Keeping with the server-side code for the moment, let's alter what we currently send and shape it somewhat differently so that it's a little more helpful. Rather than using raw text, we'll now encode it with a JSON object using the stringify function. This will allow us to format our messages and extend them with added metadata, meaning we can send other bits of information, or state, between the server and client along with our message text. We'll start by adding a message property, which will use the original string constructor value and message text from the client. To accompany this, we'll also add the socket ID value to the object, so we know which client the message originated from. However, the problem here is that the client IDs are only stored on the server, and each client is currently unaware of which ID the server has given them. So for this to work as intended, we'll have to send this ID onto the client too, once it's been generated. As you can expect, the ideal place to do this would be when the client initially connects. So let's do just that in the connect client function. Here we'll now send a new response back to the client with the ID that has been assigned to it once it connected, again wrapping it within an encoded JSON object. Although as we're now sending a more complex formatted messages between the client and server, we should ideally start giving each of them a unique name. This helps to easily identify the type of metadata or shape that is associated with the message being sent. Let's add a new property called method to each of the JSON objects to hold this unique name, starting with the connect function. As such, we'll give this message the name of connect, so that the client knows this is a response to the connection. Then in the handle client message function, we'll give this message a method of, yep you guessed it, message, so that the client knows that this message is a message. Okay, let's now move over to the client code and change how it handles the messages based on these new method types. Inside the handle server message function, we'll first deconstruct the method property from the event data, which we'll now have to pass from the JSON object string. We'll also spread any other properties within that object into an args value. Then we'll create a switch block and take our current message code and simply move it under the message method case, not forgetting to update the inner text to the args.message value instead, as this is now where the chat message resides. This should now replicate the changes we made on the server. While we're here, let's also add and handle the connect method case too. As this message now sends the client's ID, we'll create a client-side state object similar to what we've done on the server. This will only include the ID property for now to store the client ID value received from the connect message, which was allocated by the server. We'll set this to undefined initially, but set it to the args ID value under the connect message method case in the switch block. Good stuff. Both messages are now handled correctly within the client. Let's next update our UI code so that the correct styling is used when a chat message is received. As we're now sending the originating client ID with each chat message, we can compare that value with the stored ID we now have in the client. So under the message method case, let's do this and return the correct CSS class based on the result. If the IDs match, this would be an outbound message, otherwise it will be an inbound message. Just for reference, both of these classes match the test messages we set up originally. Finally, we can replace the hard-coded outgoing class with this new value. Okay, back in the browser, let's test this again by sending another set of hello chat messages from each window. And just like before, the messages are being received by both clients, but now have the correct styling being applied based on where the message originated. We can double check this by opening up the DevTools and debugging the messages as they are received. Notice how I've attached a breakpoint to the switch block here, so that I can examine the message data and its properties. And it would seem that both message types are working as expected. Nice! Back to the HTML code. As we have the basic messaging now working as intended, let's finally remove the test messages we had initially, as they are no longer required. While passing client IDs around is well enough from a technical point of view, users of chat applications will generally sign in with their user profile. These include certain details associated with them, although specifically for a chat app, this will be their avatar name. So in the client code, we'll start by adding a new property within the state object to store this provided name. Whereas I won't get into setting up user contexts, handling security, and/or authentication tokens in today's video, having a secure way of handling user data is definitely something you should implement in a production application. For today, however, we'll sidetrack the sign-in process and take the easier route, just so we can prove our point and goal. Instead, we'll simply retrieve the username from the URL of the application using standard URL param values, as you can see here. We're using the key or variable name of user, along with the name value after the equal sign. Note the question mark after the URL, as this is used for the delimiter for the URL and param values. With that in place, in the client code we can pull this param value from the address bar when the page loads or refreshes. So for our new username property, let's get this by using the Windows location object using the URL search params property. With this, we can retrieve the name value using the key we've used, which we know is user. Keeping with the idea that the server is the source of truth, we'll also need to send this name onto it once the connection has been made, extending the initial handshake somewhat. The advantage here is that if the URL or username changes, they would have to refresh the page, and therefore would have to reconnect to the WebSocket server. So let's update the connect method handler by sending another message to the server, so that it can associate the client ID with the entered username. Notice we're following the same practice as before by wrapping the message within a JSON object and adding a method name. I've called this one register, as we're registering a new username. Back on the server, let's now update the code in the same way as the client, so that we can handle these new message shapes too, including our new register method. In the handle client message function, just like before, we'll pass the raw data from the JSON object and deconstruct the method name and spread the other properties into an args object. Then set up the switch block to handle each type of message, using the method value. We'll first move the current message code into the message method case, not forgetting to update the message with the new args property. Then we'll add a new case for the register method we just created. Here we'll simply add the username args property received from the client to the assigned WebSocket on the server. And just to tie everything up, we'll send the username with each chat message too. We'll also align the handle send message function within the client, so that its send function also uses the correct message method within the JSON object too. Oh, and just before we test this, while we now have the username on the server, let's now update the server's login messages to now use this name too if we have it. Okay, back in the browser, let's again send a couple of chat messages to see the results. Notice that I've also added a new username to the other browser window too, using the URL param just as before. As the clients connect, the username is being sent to the server, and in turn storing them with the associated WebSocket and ID. Then when any chat messages are sent, the server now uses and logs out the username instead. If we were to open yet another instance of the application, you notice this too also works as intended, with its messages and username appearing in the server log. Great stuff. Although rather constantly looking at the server logs for who sent the message, chat applications usually display the user information in the UI too, along with the chat messages. So let's also replicate that. In the message method of the client code, we'll start by changing the inner text property to use an inner HTML property instead, as we'll want to add a number of elements to the UI this time around. We'll move the actual message text to the new div element and give it a new class called bubble. This element will eventually replicate what we have already. However, underneath this, we'll add another div that will contain the sender's details. I've included both the username and the time here, which to be fair, we don't have the latter in the args object just yet, so we'll need to add that to the JSON object on the server. Before we do that though, let's update the style CSS file with the new classes and styles that accompany these new divs we've just created. Again, I have these already prepared, so I'll just paste those in here. Please go ahead and pause the video if you wish to copy them. Okay, finally we'll jump back to the server code and update the JSON object with the missing time property. We'll use the install constructor object that is provided by both NodeJS and the browser to create and format the date and time. For anyone who's done date or time programming before, you'll know these can be especially a nuisance to develop for, so having access to this object can alleviate some of those pain points. We'll use the default locale so that any formatting will default to your local OS's preferences, which for me will be GB or Great Britain. We'll set all the time parts to be numeric to keep the formatting short, and finally we'll use this to format a new date object, which will use the current date and time as the base. If we were to bring up the same three browser instances and send a message from one of them, you should now notice the message includes a username and the time it was sent underneath, just as expected. This should work for all the connected clients and be presented in their chat windows. Nice. One thing you may have noticed is that the chat window will start to scroll if the messages exceed the height of the window. This is the normal behaviour, although this means the last message will become hidden, meaning you'll have to scroll the window down to see it. Usually chat applications accommodate for this, so let's quickly add a simple enhancement to solve it in our app. In the same message block of code, just before the break statement, we'll use the scroll into view function on the newly created message element. We'll give this a setting object with a block value of end and a behaviour value of smooth. This function will attempt to smoothly scroll the parent, which is our chat window, so that this new chat element is in view, which gives us exactly what we want. Jumping back to the browser now, we'll fire a large number of messages into the chat window to force it to scroll. You should notice once the messages exceed the chat window's height, the last message will scroll into view, removing the burden of scrolling down manually. Excellent! With this, we pretty much have the basic functions of a chat application now. Although for the last part of this video, let's add some smaller enhancements to move it closer to what you see in larger chat applications. As we seem to be building a group chat application, let's start by adding some global join and leave messages when users leave or join the page. We'll start by broadcasting a join message to all clients when a new user connects or registers with the server. So in the server code, in the register method, we'll simply add another call to the broadcast message function, using another unique method following the same pattern as before. I fully enough call this one join. With this, we'll just send the username associated with the client registering. Then within the UI code, we'll create another new switch case to handle the new join message method. Here we'll also follow the same exercise as below, creating a new list item element and adding the required styling via a CSS class, which in this case is called notification. Then we'll set up its contents with the inner HTML property again. This simply adds a div element along with the text that describes a new user has joined. This message includes a username that we can pull from the args object. Then finally, we'll add this to the DOM using the append child function, and again scroll the element into view using the scroll into view function. And just before we test this, we'll copy over the small amount of CSS styles into the CSS file to cover this new element. As per usual, go ahead and pause the video if you wish to copy this too. Opening up the free browser instances, once we refresh each page, the first thing you'll now see is the has joined message for each user as they connect to the server. These messages are also mirrored across all connections and windows. Okay, good stuff. Let's do the opposite now and send a similar message when a user disconnects or leaves the chat. In the server's socket events, you'll hopefully remember that we already set up the disconnect event with a disconnect client function callback. So in this function, we'll again broadcast another message to all clients that this user has left the chat. For this message, we'll use the method name leave, and again send through the associated username from the WebSocket that has disconnected. With this set up, we'll again create another switch case to handle this new method in the client code. In fact, let's just copy the join method's code and update it where necessary, as for the most part, it'll be the same. We'll basically just change the element name and the message displayed within the browser. Opening up the three same browser instances again, let's now refresh the page on each window separately one at a time. You should now notice once you do that, the other chat windows will show the user leaving and rejoining as they disconnect and then reconnect to the server. We should also see the leaving message by closing a tab, window or moving to another URL, as shown here. Good stuff. Okay, for the next enhancement, let's show some more information about the chat itself, such as the title and its members. We'll start by adding a header to the HTML file, above the current chat window div element. This includes two elements, a title and a members div. As you probably guessed, this section of the HTML will display the title of the chat window and the number of members currently in the chat. As both of these values will be stored on the server, we'll set the content of these elements with some default values for when the page initially loads. We'll eventually look to update these with the correct information when the client connects to the server. As both of these elements require new CSS styles, let's next add those to our CSS file too. With those in place, let's have a quick look at this before we continue with the code. Even though we don't need a title as this will eventually get replaced by the server, we'll add a basic one here so we can test the styles we've added. Returning to the browser, you'll notice the page now has a header container with the title we added along with the member information as expected. Okay, let's now update the server with this information so that the client can retrieve it and update this section of the UI with the actual values. Within the server states object, we'll add a new property called title and give it a suitable chat title name. This is the value we'll be sending on to the clients once they connect. So in the connect clients function, within the WebSocket send function, we'll include and pass on this new value from the state object. To add to this, we'll also pass on a clients object that includes all of the currently connected client names. Both of these values will be used to populate the header section we just added to the UI. So to do that, back in the UI code, we'll first create a reference to the header element so that we can manage the elements in this section of the DOM more easily. Then within the connect message method, we'll get the title and member divs using a query selector from this reference. We'll then set the inner text of these elements with the corresponding arg values we've added to the new message. Note that we've used the length property of the client object to get the number of currently connected members. With another quick test of the browser, you'll notice the header section in our UI now updates with a title and the amount of chat room members once any new user joins the server. This works great. However, we currently have not catered for members who leave the chat or when users join a current session, as you'll notice the members total doesn't keep in sync. Let's resolve this too. In the server code, we'll simply copy the client's property value we just added and paste them to both the join message in the register method and again within the disconnect client's function's leave message. And just to keep the client in sync, we'll next mirror these changes to the client code too, copying the members inner text setter to both the join method and the leave method. As we've added this to the join method, we should probably remove it from the connect method now, as the join message method comes straight after the connect method as part of the initial handshake, meaning we will get this update there instead, removing the duplication. And again, to keep the server in sync, we'll remove the corresponding property from the send function within the connect client function. Checking the results in the browser, we can see that the member's total value is correctly updated and kept in sync as users join and leave the page. Great! Okay, with that working as intended, let's move on to the last enhancement for today's video. A live update message detailing which client is currently typing a chat message. a feature that you commonly see in other modern chat applications. As we've done previously, we'll start by adding the required elements to the HTML file. This includes a span that we'll use to display who's currently typing, and 3 further spans, which we'll style and animate and call them blips. This applied motion gives the impression that this is a live notification to the user. Also, notice that we have a hidden class here, which we'll use to toggle these elements on and off as necessary. Then within the styles file, we'll then add the accompanying CSS styles required for these new elements. This includes the typing class, along with its nested classes such as the styling for the blips. Speaking of which, we'll also need to add the animation keyframes for their animation, which we'll do at the bottom of this file. To prove these are actually working correctly, we'll first have to comment out the hidden class styling. As mentioned, with this now disabled, we should be able to see what was added. So let's quickly do that by moving back to the browser for a second. Great stuff, we now have a message underneath the chat window, informing us that supposedly someone is in the chat typing a message. Alongside this, we have the 3 blips animating, or bouncing up and down, giving the impression that something is happening in the background. The idea is that we'll hide this message when nobody is typing, but re-show it when someone is actually typing, informing everyone in the chat. Let's jump back to the code and add this special type of event. First, let's remove the comments we added around the hidden class in the styling file, so that the message block is hidden by default. Okay, in the client code, we'll next add a key press event to the chat message box, and give it a callback function. If you're not aware, this event will fire each time the user presses a key inside the input field. Next, we'll add the callback function stub, but before we can implement that, we'll have to set up and configure several things first. While we're in the client code, at the top of this file, we'll start by adding a reference to the typing class, which we know is a wrapping container element for the isTyping message block we just added. We'll be using this to toggle the hidden class we just talked about. We'll also add a new property to the client state object, called isTyping, with an initial value of undefined. This variable will hold a reference to a timeout ID, which will be used as a time window for the key press events. We'll be tying this to the toggling of the hidden class on the typing message elements. The general idea is that each time a user presses a key, this timeout will be reset, keeping the window open and leaving the message visible. However, if they stop typing, the timeout will expire and therefore hide the message. Back in the key press event callback function, let's now go ahead and set this new property with the setTimeout function. For this, we'll give it another callback and a window of 2 seconds, or rather 2000 milliseconds. We'll create this new callback, which will be called once the timeout is completed, which we know will be when the user has stopped typing. So inside this, we'll simply set the state's isTyping property to undefined again. Then inside the key press event callback, we can now check to see if this property is defined or not, and if it is, we can clear and reset it using the timeout reference we've assigned to it, meaning the line we added below will set up another instance of the timeout, causing another iteration of the delay. However, if the timeout is undefined, we'll now send a new method message to the server, called typing, to sync these details with the server. Following the idea that the server is always the source of truth, we'll simply use a state's arg property and set this to true, meaning this user is currently typing. On the flip side, in the clear typing state function callback from the timeout, we'll copy this send request, but this time set the state property to false, meaning the user has stopped typing. Let's now set up this new message method on the server. In the handle client message function, we'll add a new typing method and add a call to a new function that will handle the message, passing on the socket reference and arg state value. Inside this new function, we'll follow our usual process by logging out a message to the console, describing whether the user is currently typing or not, using the details we forwarded. Then we'll update the socket reference with a new isTyping property to hold the current typing state received from the client. On the back of this, we'll now collect and build a list of clients that are currently typing using the filter function on the client's array, before mapping out the actual usernames associated with them. Once we have this information, we'll finally broadcast back the typing method message to all clients with this list of usernames. To finish up, let's update the UI based on the new typing method message from the server. As per usual, we'll add the method to the handle server message function and first check to see if the usernames array contains any users. If not, we can assume no users are currently typing, and therefore simply add the hidden class to the typing message UI element and exit early. Otherwise, we know someone is typing, and therefore can remove the hidden class from the typing message UI element. Next, we'll then update the first span element within this element, using a query selector with the user details from that array. As we have a list of names, we can simply use the join function using a comma separator here to convert the array of names into a readable name string. Okay, with all that said and done, let's open up a browser again and see the results. You should now notice that when a user starts typing in the message box, the isTyping message will appear with the name of the user currently typing underneath the chat window. Once they finish typing, this message will disappear as expected. Using multiple browsers at the same time, you should also notice the message displays all the relevant names. Nice. although we do have one slight issue. The typing message will still hang around when the chat message has been sent. This is a side effect of the timeout function we're using. So for the last change today, let's quickly fix this. In the client code, within the handle sendMessage function, we'll clear the timeout using the state isTyping property and make a call to the clearTypingState function. By doing this when the server sends the message, we can guarantee that we reset the typing state for the user. With the final check in the browser, once you send the message, you should notice that the isTyping message is instantly hidden and removed. Excellent! I'd say we now have a somewhat complete, while rather basic, chat application. If we wanted to, we could actually continue with this and expand on it even further, adding such things as a proper user logon screen, sending other types of messages such as images or rich formatted text, include other chat rooms, or even react to certain messages using emojis for example. But these are beyond the scope of this video, so I'll leave those to you, as I'm going to leave it here because this video is getting rather quite long. Just before we finish though, I will mention that the code to this project will be available to all my Patreons this month, where I've cleaned up the code somewhat and added several other enhancements not seen in this video. So if you're interested in that, why not visit my site over there and see what you're missing out on. To recap though, we've learned the basics of what is necessary to implement WebSockets in an application. We've also created a server and decided it would be the source of truth for the connected client. Furthermore, we've come up with a method messaging system that allows us to send rich events where both sides can react as necessary. Most of what we've done today can be used as foundations and applied to other online communication scenarios on the web, where real-time messaging is required, which as mentioned, for my channel is online multiplayer gaming, something we'll pick up in a future video. We could have also defaulted to a more thorough library too, such as Socket.io in both the client and server, but as with most of my videos, I generally prefer to be agnostic and keep my projects as lightweight as possible. I'd also much prefer to try and understand the underlying technologies too, which you can only really do by skipping such libraries and/or frameworks. And finally, I'm interested in hearing what you think about this one, as it's somewhat of a departure from my usual content on this channel. Would you like to see more full stack or front end content here? I'll leave that one with you. As mentioned, hopefully you can see why I felt this video was important to stray from my gaming content, at least initially. Don't worry though, we'll be jumping straight back into gaming content very soon. Either way, thanks to everyone for watching, especially for those of you who have gotten this far, as I know people tend to drop off way before this part of my videos. You're the ones that keep me going. And with that, I'll hope you see you in the next one. And out.